Dear students, you all know the procedure for tracing a curve whose equation is given in Cartesian coordinates. Let us quickly revise the procedure for tracing the curve. So first, we would like to determine the symmetries of the curve. So we would like to know whether the curve is symmetric about the coordinate axis, namely x-axis, y-axis. Also, we would like to know do we have any other lines of symmetry, say for example y equal to plus minus x. Next, we wish to know whether origin lies on the curve or not, and if at all origin lies on the curve, we would like to know what are the tangents at the origin. Next point is to determine the points of intersection of the curve with the coordinate axis, x-axis, y-axis, and any other lines of symmetry for the curve. Whichever points we are getting here as the points of intersection, we will also try to determine the nature of tangents at these points. Also, we will try to find the tangents at infinity to the curve. We call tangents at infinity as asymptotes to the curve. By studying the nature of the equation, we will try to determine the region of presence or absence of the curve. By using this procedure, let us sketch some of the curves. So first, trace the curve whose equation is x square y square equal to a square into y square minus x square. Note that the given equation can be written in the explicit form as y square equal to a square x square upon a square minus x square. This equation, as all of us can see, contains only even powers of both x and y, because of which the curve is symmetric about x-axis as well as y-axis. In equation 1, if we substitute x equal to 0 and y equal to 0, equation 1 is satisfied. Therefore, origin lies on the curve. Tangents at origin to this curve are obtained by equating to 0 the lowest degree terms in the equation. The lowest degree terms in the equation are a square into x square minus y square. We will be equating these lowest degree terms to 0. So equations of tangents at the origin are y equal to plus minus x. Now we wish to determine the points of intersection of the curve with the coordinate axis. For determining points of intersection with x-axis, if I substitute y equal to 0, I am getting x equal to 0. Similarly, if I substitute x equal to 0 in the equation, then I am getting y equal to 0. That is, in other words, origin is the only point of intersection with coordinate axis. Now we wish to determine the asymptotes. So that means we wish to determine the tangents at infinity to the curve. For determining asymptotes parallel to, say, y-axis, we equate to 0 the coefficient of highest power of y in the equation. Coefficient of highest power of y in the equation is a square minus x square. Therefore, x equal to plus minus a are tangents to the curve at infinity, that is, they are asymptotes to the curve which are parallel to y-axis. For determining asymptotes parallel to x-axis, we will be equating to 0 the coefficient of highest power of x. Coefficient of highest power of x, as all of you can see, is a square plus y square. If we equate it to 0, we get y equal to plus minus a multiplied by I. So that means we are having imaginary tangents. So that is, in other words, the curve possesses no asymptotes parallel to x-axis. For determining the region of presence or absence of the curve, observe that the xy plane is divided into 4 vertical parts. So this is my x-axis, this is my y-axis. We said that x equal to a and x equal to minus a are asymptotes to the curve which are parallel to y-axis. Therefore, we will be considering this strip from minus infinity to minus a to 0, 0 to a and a to infinity. Observe that for minus a less than x less than a, y square is positive, while for minus infinity less than x less than minus a and a less than x less than infinity, y square is negative. Therefore, the curve completely lies in the range minus a less than x less than a. So by using the observations, the approximate shape of the curve is given by so this is my x-axis, this is my y-axis. This line is x equal to a, which is an asymptote to the curve. This line is x equal to minus a, which is again an asymptote to the curve. Also, this line has equation y equal to x, which is tangent at origin to the curve. This line, whose equation is y equal to minus x, is tangent at origin to the given curve. Therefore, the shape of the curve, so here I am having x equal to a to be an asymptote, here I am having a y equal to x to be tangent at origin. So shape of the curve is as shown in the figure. It is important to note that we should be drawing the figures by using pencil, and it is necessary to label all the points, all the parts in the figure. Now let us move ahead to the next example. Trace the curve whose equation is y square equal to a cube x upon a square minus x square. I can write this factor a square minus x square in the denominator here so as to have the explicit form for the equation. This equation contains odd and even powers of x but contains only even powers of y, because of which the curve is symmetric about x-axis. It is very easy to see that origin lies on the curve and equation of tangent at origin is x equal to 0. That means y-axis, which we have obtained by using the Newton's method. So that means equating to 0 the lowest degree terms taken together in the equation. So lowest degree terms is a cube x. We have equated it to 0, getting x equal to 0. That means y-axis as tangent at O. In the equation, coefficient of highest power of y is y square, coefficient is a square minus x square. Therefore, equations of asymptotes parallel to y-axis are given by x equal to plus minus a. The curve is intersecting coordinate axis only at the origin. For determining the point of intersection with x-axis, we substitute y equal to 0, getting origin to be the only point. Similarly for y-axis. Now for determining the region of presence or absence of the curve, we are having the xy plane. So this is my x-axis, this is my y-axis. We are having x equal to a and x equal to minus a to be asymptotes parallel to y-axis. So for minus infinity less than x less than minus a, so that means this sector we are having y square to be positive. Also for 0 less than x less than a, so that means this sector we are having y square to be positive. On the other hand, for x lying in the range minus a to 0 and 0 to a, we are getting y square to be negative. So here we are having y square to be negative, here also y square is negative. Therefore, the curve completely lies in this sector and this sector, and it is totally absent in this sector. Therefore, the conclusion is the curve completely lies for minus infinity less than x less than minus a and 0 less than x less than a. So I also can say that the curve is a disconnected curve. By considering these properties that we have discussed, the shape of the curve is given by so this is x-axis, this is y-axis, curve is absent in this sector, curve is absent in this sector. So curve is present here with the properties x equal to a asymptote, x equal to a asymptote, tangent at 0 y-axis, so tangent at origin is y-axis, and in this sector we are having y equal to 0, that means x-axis asymptote and x equal to minus a an asymptote. So shape of the curve is as shown, as drawn in the figure. In the next lecture, we will be discussing about curve tracing again for Cartesian curves but with oblique asymptotes.